first area. The objective of this workshop, 3 days workshop, is to cover the thrust area in latest industry innovative complex problems may try to solve through the quantum computing. The distinguished academic experts and a panel of experts from the industry has been called to share their perspective in the current state of technologies to harness the power of quantum computing in the long term with all our participants. So for this 3 days workshop, our distinguished speakers, Mr. Christopher Coleman is a postdoctoral fellowship at Stewart Blusson Quantum Matter Institute, University of British Columbia, Canada, and Mrs. Bhavana Killambe, the software engineer at ARM, London, and previously she worked in the IBM ISL lab with the quantum machine learning. And Mr. Abhishek, tomorrow's session, Mr. Abhishek Sharma, the object automation training, and Professor Sadhyanathan from the KLE Technology University, and Professor Mr. Arshad Mohammed, technology expert in Oracle, and previously worked in the IBM software lab in the quantum machine learning and other things. I welcome all the experts going to be delivered the next 3 days for our faculty members and as well as the research scholars. This is the current area, the quantum computing. Many of the researchers, they started working on the quantum cryptography, quantum machine learning, quantum deep learning, quantum convolution neural network. All the soft computing is taking place with the quantum. So you can see after attending this workshop, definitely you will be getting benefit with you can come with the good research papers and as well as some of the work. And here in industry scenario, the IBM has started working. The entire the India, I think they invested more money on especially on the quantum computing, and as well as the IBM, Google, all industry giant has invested more money and they created their own software for the quantum computing and so on. I think in this 3 days, we are going to see how they have been incorporated, how our classical computing mechanism is incorporated with the quantum computing, how the transmission is taking place, and the basics knowledge and hands-on will be taking place in the entire 3 section. So here, your active participation is very essential, important throughout the session. So I think we have taken in the right way, and I think I thank all the once I figured immediately Sir has sanctioned and is given a platform to give this opportunity for collaborating with IBM and Open Power. So on behalf of the entire committee, I welcome once again to all. Thank you for giving opportunity. Thank you.
Thank you, sir, for the fond greeting. Now, I welcome our principal, Dr. D. Vasudevan, sir, to deliver the presidential address. Welcome you, sir.
Respected guest of the day, Mr. Ganesan Narayanaswamy, IBM Global Leader for AI and Cloud Enablement and Ecosystem for IBM Power Open Power Systems. Dr. A. Vincent Anthony Kumar, who had given a nice welcome address, and also he had delivered a overview of this entire program. I am much happy indeed to be presiding over this type of reputed international workshop on quantum computing, which is done along with IBM Open Power and Object Automation, and our faculty members, students, and other participants from academia has to take this very effectively and leave this workshop with a lot of takeaways. Moreover, this type of exposure to international status on current technologies such as quantum computing is very important, especially for us because we are working with a vision of making our students into a globally employable engineers. For making them a globally employable engineers, the global awareness on technologies is very, very important. And this is the right platform, and IBM is the right industry to deliver these things to our faculty, students, and academia in this part in general. I wish this workshop a great success. I take this opportunity to congratulate the HOD of Information Technology and his faculty team and the student team who had worked tirelessly to organize this type of international workshops. I also thank Mr. Ganesan Narayanaswamy, IBM Global Leader for AI and Cloud Enablement, for his continuous rapport with us and continuous support to our institute. And his name became one and same with our institute because of his continuous participation and continuous encouragement in our campus activities. And I also thank the speakers, reputed speakers who had given their consent to address in this workshop. I take this opportunity to thank Dr. Christopher Coleman, Dr. Mrs. Bhavani Kilambi, and Mr. Abhishek Sharma, Professor Satyadam Sikaru, and Mr. Arshad Muhammad, who had given their consent and who are going to deliver their addresses in this 3-day workshop. I wish this workshop a great success and also request our students, faculty, and the academia to utilize this platform more effectively and should leave this workshop with a lot of takeaways, which will enable them to have good research, good thesis, good projects in their academic career. Thank you very much. All the best for the workshop.
Thank you, sir.
Thank you, sir.
Thank you, sir, for the inspiring speech. On behalf of PSNE College, I welcome our chief guest, Mr. Ganeshan Narayanaswamy, who is a global leader for IBM company. I welcome you, sir. Here is your speech.
Thank you. Thank you very much. This is not the first time, we are doing, the workshop for PSNA. We have been collaboration with PSNA for last, I would say 7 to 8 years. Started with a big data workshop with my team back in 2014 or 2013, actually. So from that time onwards, I've been, globally enabling many workshops, many enablement programs, and also solution development and setting up center of excellence, where I want to basically, grow the clients as well as, the partners who are, investing time in the technology. The technology, what was there before and what is there now, it's all similar, I would say. Only thing is, the growth happened, in computing and storage. Because of that, the things are changing right now to utilize, those features. We are talking about, the classical computer and, which gives the computing, and also the quantum computing, which is going to, which has been, providing, kind of a platform for, giving a super fast, computing, and the storage. The storage is very important for AI kind of, the operations. And, right now we are talking about petabytes and exabyte. Even in an iPhone, I do see 1 terabyte of storage available right now. You think about it, 20 years back, getting a 1 GB of storage or 10 GB of storage was very difficult. and things transformed, in such a way that you will get, large compute and large storage for you to go and, do the, the programming and, programming. When I talk about programming, it's all about algorithms, and algorithms based on, the mathematics, the formula, such as a linear algebra kind of, equations and all. So these are all, tied together, when I say something. And that's where, I'm actually, trying to put together a workshop also this time to combine, to talk about, the computing, the superior, advantage of, the computing, the quantum hardware, where Dr. Chris Coleman from UBC is going to be spending good amount of time with us, on that. And, it's a great opportunity for you all to learn about what is the hardware behind quantum and how that is going to be evolving, and what are all the features, going to be applied, to the hardware, to make it more powerful. So be proactive on, asking questions and all. This is not a, a simple workshop, where you just wait for a certificate, to come. It's an opportunity for you to build, the future world. In next 20 years, certainly the quantum is going to take a lead role, and around quantum there will be a lot of enablement in the ecosystem, like a programming and, the storage and networking, and many things, will form also. All these things, one can learn from the basics and, build upon it. And when I talk about, all these features, there are, 6 to 7 areas where I always, want to recommend, the students, faculties, and developers in today's world, to work on. The first one is right now, the most trending one is AIoT, artificial intelligence of things, where there are a lot of, things, happening around the world right now. People are, working on, developing a edge kind of device, and, several, small and medium devices to add, the AI kind of feature, as part of that and all. And then, the second one, I would say hybrid cloud, where AI and high performance computing going to be playing a key role in both, the cloud as well as on-prem systems. So one has to learn about that. We do have all the, the courses, curriculum, solution development, even, remote internship, kind of stuff also. And then everyone, talks about, the AI, but there is something called enterprise AI, which is very important, because the data, the valuable data, is available only with the enterprises. When I say about enterprise, one example is bank, where, the banks have got a real data where, the customers, do get involved in a lot of transactions and all. And with that data, what one can do with the enterprise, what one can do with AI. And that's where, we are actually putting together kind of, a good curriculum and workshop, as well as solution development on that. And then the fourth one is cyber security. You guys definitely know that, there are a lot of attackers always try to, focus on, stealing money and stealing, some kind of a confidential data and all the stuff. It's all happening around the world. I would say, like, there are like 200 plus countries everywhere. The cyber crime is happening. So that's where the cyber security is very important. The cyberspace related activities are very important. And, we are working to create cyber hub, and, even the diploma in cybersecurity, and also how one can develop some instructions at the hardware layer, so that the system, the computing can address during, processing the program also. So all these, things, could be put under, the cybersecurity with the AI kind of feature. So the four things I said so far. And then the fifth one is accelerators. So the quantum is one of the accelerators, of course, but there are, like, accelerators, which could accelerate in addition to the CPU in the system too. And I would say, like, FPGA is one of the accelerator, the GPU, the other accelerator, like that. There are a lot of accelerators that are coming to the market, and you guys have to study about it. These are all interconnects, with the computer. And of course, the quantum computing is the era, like, is the area where definitely, people are investing time on it. Right now, IBM as a company, we basically have quantum computers installed in US, Germany, and Japan. And there are other places also we are working with, to see how we can, install the quantum computer and, develop some new solutions as part of that. So I'm all like, waiting to, waiting for a big challenge, on the quantum too. And setting up quantum hubs and, even diploma courses and, the solution developments in quantum. There are so many industry areas where one can, develop the solutions with quantum too. These are all the things, very important for your career. All 6 things, whatever I said: AIoT, hybrid cloud, enterprise AI, cyber security, accelerators, quantum computing. All these 6 areas, if you focus on, some of the activities, your career will be really good, and you will end up working in a, top 10 companies and, develop, very good solutions too. So as part of today's, the program, like, I know the 3 days program, but today's program and then the next 2 days, we have very good, content, as well as the very important speakers who are going to be sharing, some of the good technologies. Today, we will be covering, mostly hardware stuff, the quantum hardware, and also how one can get access to the quantum and all the stuff. There are 2 speakers, both are from, abroad. One is actually from, Canada, the UBC, University of British Columbia, one of the best institutes in the world. And, Dr. Christopher Coleman, who has done his PhD from South Africa, is doing his postdoc here in UBC, and he has done a very wonderful work in quantum for the last 10 years. And he's going to be sharing some important stuff, followed by Bhavana Kalambi, going to be talking about our experience, our journey in quantum. That's going to be an interesting one for students and faculties, who can start their journey, as we speak today. And all together, we organize in such a way that, hardware you're going to get today. Tomorrow, people are going to talk about the programming, the programming model, Python and linear algebra and all the stuff. And the third day is going to be all about algorithms. Without that, like, you cannot, do anything. So algorithm with, the linear algebra kind of, the concept, everything, will be delivered. So think about it, this programmings and linear algebra and, the algorithms need not have to be only for quantum. It could be applied for any other technologies. And that's a fundamental thing, one should learn about it. So this is a great opportunity for you all to be part of this. I see right now there are like 215 people join this, the workshop. I'm really happy about it. The starting of the year, the first workshop, and with the classical computing, as well as the classical computing platform, the Python and programming model and algorithms on a quantum hardware. How is it? The stack is going to be vibrant, and we can do lots of research and development activities on this platform. Papers, presentations, publications, international conference presentation, so and so things one can do with that. With this, I'd like to invite our first presenter, Dr. Christopher Coleman, who is going to be sharing some of his 10 years experience on the quantum side of the hardware. Welcome, Dr. Chris, for spending time with us. Chris, please go ahead and start your session.
Thank you for the introduction, Ganesan, and I'm very happy to be here today. Can you see my screen?
Sure. Looks
Great.
very good.
Okay. So as Ganesan gave a very good introduction, my name is Christopher Coleman, a PhD holder. I'm originally from Johannesburg, South Africa, where I was involved with setting up some of the country's first quantum computing programs. My funding came directly from the Research Foundation of South Africa, and I work primarily on measurement and control systems for quantum technologies, on quantum matter systems like diamond, nanoelectronics, and testing out these different platforms and incorporating them into next generation technologies for the quantum revolution. More recently, I moved to Vancouver, Canada, to pursue an academic research career. And this is also within the realm of control and measurement for quantum technologies and quantum systems. And that's where I am currently based. I do, however, have several activities in the realm of quantum algorithm development and overall have good interaction with the local industries here in Vancouver around applied quantum computing and various startup activities. So the talk that I'm going to be giving today, I think, is very much suited to what Ganesan was speaking about earlier. We know that the quantum computing revolution is already underway. It's a very vibrant and immersive experience. There are a number of different technologies being explored right now, and several of them have already come to a level of maturity or readiness that they are commercially available. In my talk, I'm going to be taking a look at various major players in the space. For example, the larger quantum processor unit providers such as IBM, Microsoft, IonQ. I will be speaking very briefly about the different types of technologies that exist, depending on the platforms available, such as superconducting qubits, trapped ions, or photonic systems. So a very brief introduction about the quantum technologies that are already commercially available. This is all under the NISQ era of quantum computing. NISQ stands for Noisy Intermediate Scale Quantum Systems, and it is the classification scheme we have for the current era of technologies. This is in contrast to the future fault-tolerant systems. There are various advantages or disadvantages of these different regimes of quantum computing, and I will be focusing on the NISQ era today. I will also be speaking a little bit about the intersection of machine learning and artificial intelligence with quantum computing. These are two very disruptive technologies, and they have a lot to gain from each other. So I will be speaking about a few examples where we see the overlap and interference of these two computational resources. So to get into it, some basics about quantum computing that you need to know first. Quantum computing can be compared to classical analogs. I think everybody in the audience will be appreciative that, or at least have a background in some form of classical computation. We know that classically information is processed in a binary fashion with ones and zeros, Boolean algebra. However, the main advantage with quantum computing is that you are not restricted to this binary base. You can either have ones, zeros, or an infinite number of states in between these two. And this is because of the quantum bits, the qubits, that this technology is built up of. This gives an enormous computational advantage and speed up, or at least theoretically being able to do. And this is something that is actively being explored right now. So qubits can actually be manipulated in these various aspect states. And they can be in a superposition of states as well, and also abide by quantum entanglement. So thanks to the physics of quantum mechanics, there is a lot of additional capabilities of qubits and quantum technologies as a whole that classical systems cannot perform. So individual qubits are then linked together, and we apply logic operations on them to have quantum gates. These quantum gates have to follow quantum mechanical principles in how you add them, subtract them, multiply them, and entangle them. Once you have a number of gates, you can iterate and add these together to get quantum algorithms. And this is how the logic processing is brought about on a quantum processor. For example, IBM have already had several iterations of cloud-based quantum computers that are available free of access. What you see in this image over here is a 5-qubit system, which was one of the first commercially available gate-based quantum computers on the market. As I mentioned before, your qubits hold the actual information or process the quantum logic, and you can perform various gate operations or logic operations on these qubits and perform some sort of measurement which gives you a probabilistic outcome, which you can then compare to your theory, and you will know what you are computing. This is an example of a circuit that has been built up using IBM's Qiskit, which is a very valuable resource for anybody trying to get into the basics of quantum computing. Now, as I mentioned briefly already, there are several types of different technologies for quantum computing that already exist. These are being explored by several very heavyweight, high-profile companies, and the different quantum computers have advantages and disadvantages over each other and are sitting at various technology readiness levels. As I mentioned, today we are still under the umbrella of the NISQ era. So this is a rapidly emerging field, and there is always progress in these systems. So if you start tracking these different providers, you will see that the number of qubits, the quality of the qubits, such as fidelity, how powerful they are with algorithm and information processing, is always increasing. This is not a static field, it is very dynamic. So, doing a quick deep dive of the various quantum systems that are available. One of the very first to be developed and most popular are called the superconducting circuits. Now, one of the advantages of these systems is that they are very easy to fabricate because they rely heavily on the same processes that are used in the semiconducting industry. However, the disadvantage is they have a very large footprint. They have the resources required to cool these systems down and operate them are very high. This is because we're dealing with superconductivity. Superconductivity is a very low temperature physical phenomenon. So if you develop a circuit or some logic element based on superconductivity, you need to cool this down to below 100 millikelvin, typically tens of millikelvin. This can be very expensive. However, it is one of the most popular commercially available technologies right now. IBM, Google, as well as Intel have their own superconducting circuits. There are several startups that have already emerged, and we are talking about multi-million-dollar investment startups, such as Alice & Bob, based in Paris, Rigetti, Berkeley, California, and several others that you can find information on. Another very interesting modality of quantum computing are the linear optics and trapped ions. These are very interesting systems because instead of relying on solid state hardware, such as circuitry that we are used to and what we conventionally think of when we talk about a computational device, these rely on laser beams and trapped ions. Essentially, any type of electronic control is substituted with laser or light, and this uses things like single photon detectors, and optical control of individual atoms or ions which are trapped inside capsules. So individual atoms here actually make up the qubits, and you can entangle them and you can perform logic operations, as I mentioned before. This is a very popular technology, and there are at least 4 different trapped ions commercially available right now. For example, with IonQ and Honeywell, these are some of the biggest examples. A very good example or an advantage of trapped ion systems is that they have extremely long coherence time. Now, the coherence time is basically the time that you can keep the quantum state alive in order for you to perform your logic operations. This varies from the quantum state that you're using in your quantum computer. Trapped ions have some of the longest coherence times. This is typically seconds to minutes. However, because they are relying on laser beams and the hardware associated with that to perform the logic operations, the gate speeds are significantly longer than other technologies. This is in the microsecond regime. This is relatively long when you compare it to something like a superconducting qubit, as these typically operate in nanosecond regime, so a very high frequency. So these are various advantages and disadvantages that need to still be worked out between the systems. Linear optics sees a combination of both photonics, so light, as well as solid state technology. Essentially, this relies on a technology known as integrated photonics. So a circuit, which is basically consisting of waveguides and optical detectors and optical components, performs the logic operations. And here, single photons are being trapped and maneuvered on this chip. This is a very early stage technology. However, having said that, there are at least 2 or 3 companies that have commercially viable products, or at least some version of a QPU online. A very good example of this is the Toronto-based company Xanadu, who have a full stack solution from AI, their own software to run the system, as well as the hardware that I have just mentioned. I would say that those are the 3 most popular types of quantum computers currently available. However, there are a multitude of other types of systems that are at various commercial viability. Intel, as well as Microsoft, have both invested heavily in quantum technologies. Intel are looking specifically at solid state technology, which complements their semiconducting industry. These are something known as spin qubits, which is essentially a semiconducting technology which is gate-based. An advantage of this is that it can be easily interfaced with existing CMOS tech, making CMOS controllers and the control of the quantum computer essentially a lot easier. However, there are many barriers to this technology which have not yet been overcome. One of these is the difficulty in scaling these systems. Qubits are very, very complex devices, especially when compared to transistors. So there are many open questions into how to actually couple multiple arrays of qubits together, especially when you start scaling up past 100 qubits or 1,000 qubits. It becomes very difficult to try and integrate the different qubits together in a way that you can still entangle them and perform your quantum mechanical operations and do your logic processing. This is one of the biggest setbacks with solid state spin qubits at the moment. But as I mentioned, many companies or corporations are actively investigating this. One of the last types of qubits that I'd like to mention here on this list are the Majorana qubits. This is a very exotic type of system and currently only being pursued seriously by one corporation, which is Microsoft. Majorana fermions is an exotic type of particle which can exist in certain superconducting, semiconducting hybrid systems. The way that this technology works, or is supposed to work, is that in these devices you can form this Majorana fermion and trap it and use this as a quantum state to perform logic operations. The major advantage of a Majorana qubit is that it is supposed to be topologically protected from dephasing. In other words, once you have trapped or condensed this quantum phenomena, it does not easily decohere or die out. This means that it has a far longer coherence time than any other type of technology. and it will be robust to environmental effects. Having said that, because this is such an exotic state of matter, it is very difficult to engineer and very elusive and difficult to measure. And there are still many teething problems with this type of technology. So just to give another comparison of these different forms, this is a visual comparison of the different types of QPUs that are commercially available right now. In the top right corner, you can see the IBM Hummingbird, which before last year, so 2020, was one of the largest commercially available superconducting QPUs. This was from IBM. Google Rigetti IQM, as well as Origin Quantum and D-Wave are all of the superconducting type. You can see that these are solid state technologies with qubits being linked by RF resonators. So this is all RF technology operating at very high frequency, typically around 10 gigahertz. This means that these are very fast, generally easy to fabricate, and there are many scaling barriers which have already been overcome. I don't know if anyone is familiar with this, but last year, 2021, IBM announced a 127 qubit system, which they called Eagle. This, to date, is the largest superconducting QPU in existence. Very soon after that, Rigetti announced an 80 qubit QPU. So this means that they are very hot on each other's trails, and it seems that the technology is already ramping up in terms of speed, capability, and overall size. In the bottom right, you can actually see what one of these semiconducting qubits look like, and this is a device from Intel. Now, anyone familiar with classical logic processing knows about the transistor, and that is essentially a gate and a source drain, so 3 electrodes. As you can see, a qubit is much more complex than that, and a lot more difficult to measure the quantum state, read out, and control what's happening in terms of logic processing. As I mentioned before, this is one of the main barriers of entry to this technology. Having said that, Intel already have a controller that is capable of running 124 of these silicon qubits. And this makes up one of the other domains of the cryogenic technologies. Both superconducting and spin qubits of the semiconducting type operate typically at temperatures from a few hundred millikelvin to less than tens of millikelvin. So this is a very, very low temperature, and it's difficult to operate. There is a lot of research going on to elevate the temperature of some of these operations. For example, semiconducting spin qubits have already been shown within the last year to be able to operate up to a temperature of 1 Kelvin. That's 1 order of magnitude higher than what they previously were. So there's a lot of interesting research that we're seeing in raising the temperature of these guys. Then on the photonic side, as I mentioned before, Xanadu have an optical integrated circuit. So basically, this is a photonic circuit. A laser beam can shine light, or through integrated fiber couplers, shine light on here. Single photons can be emitted and controlled by these waveguides, which basically track the photons and squeeze them between each other, allowing them to interfere and thus perform the quantum logic. There are also detectors, as well as phase multipliers and couplers on this chip, which allow you to manipulate the photon as it is shuffled about this chip and eventually read out. So this is a hybrid between photonic or optical systems and also solid state technology. This chip is typically run at room temperature, which is a massive advantage compared to the superconducting and semiconducting type, because you don't need to cool it. However, typically these systems do have single photon detectors, which require some cooling, albeit not at as low temperatures as the superconducting qubits. The other technology that I already mentioned is the ion trap, so neutral atoms. And as I mentioned, this is basically laser light that shines into a cavity which traps atoms, and you can perform your quantum operations on the individual row of atoms which are formed inside this vacuum space over there. Large proponents of this are the IonQ, as well as cold quanta, who deal with neutral atoms. And this is also a very popular type of system. Now, there are various corporations that have a range of different technologies which borrow from all these others of above. For example, one of them is Quantum, who have a semiconductor integrated optical system. Now, this is not yet commercially available, but they claim, at least according to their roadmap, that they will have a 1 million qubit system by 2030. If this does come to fruition, it would mean that they are the most successful of all quantum computing systems. However, as I mentioned, at this point, they do not yet have a prototype or at least a commercially viable product. So, as I mentioned before, this is a very interesting area of research, and there are many developments that are currently underway. I don't think that there is a single month of the year or week of the year that you do not hear of some breakthrough on the hardware side. A very good example of this is IBM, who have gone from strength to strength over the last decade in terms of their QPU solutions and how strong their quantum computers are. Last year, they announced 127 qubit QPU, which, as I mentioned to date, is the largest of these systems. This is based primarily on TSV technology, so through silicon via, in order to create a layered system that can be stacked. This allows them to push or place more qubits in close proximity to each other and couple them in ways that you can still perform logic operations. Now, this is still a superconducting circuit, so it still needs to be cooled to very low temperatures. Having said that, let's take a quick look at IBM's development over the last 5 years. As you can see, the bar chart at the back is showing the number of qubits that has been commercially available via the Quantum Experience Cloud. You can see that this has steadily increased, and to date, they are meeting every target that they have announced on their roadmap. 2022 marks now the highest number. And next year, 2023, we expect, according to their roadmap, IBM to release 1,000 qubit system. When we start talking about thousands of qubits, we are finally reaching a point where we can start thinking about serious error mitigation, or at least error control on some level. This means we are approaching a new regime of quantum computing called the fault tolerance, which is different from the NISQ era that we have been speaking about so far. What you can see here in the colored dots is a new type of technology called Cryo Cmos. This is supposed to be an alternative technology which couples to qubits in order to control them more efficiently and therefore allow for a speed up or a scale up of the systems. There are already a large number of different providers of the Cryo Cmos who are working to develop these technologies. And as you can see, they are already able to control the same number of qubits that we are seeing being provided by some of the QPU platforms. So this is a very exciting field, and we are seeing the merging of various technologies at this point. So hybrid solutions, all used to bring about the quantum revolution. So in case anyone is interested in what quantum computers actually look like, especially the ones that get cooled down to millikelvin regime, this is an example of the IBM system which they plan to develop by 2023, 1,000 qubits. As you can tell, the footprint to this is enormous. It's a very large dilution fridge because there are so many RF lines going down to control the thousands of qubits. It takes an entire room of electronics just to run this device. So in terms of footprint, this is very good, very big. However, 1,000 qubits by next year, that should be worth it. Another interesting thing about IBM before we move on is their Qiskit platform. And I think that there will be other speakers talking about this, but I just wanted to mention that this is a very important aspect to IBM's initiative. They are a full stack provider, meaning that they have the API and SDKs that allow you to access the computer. They also have their own quantum softwares which you can deploy and research around how to apply quantum computing for use case. And then they also build their own quantum computers. So they are one of the most prominent players in this field and basically have a solution for all the different problems in this area. So whether you are interested in hardware, software, or algorithm development, there is something for you to do under the IBM umbrella. Now, as I mentioned before, there are so many different types of QPUs available right now, and there are various advantages and disadvantages between them. Going back to IonQ, one of the most prominent of the trapped ion systems that we know about, they have also been pushing very heavily on their technology. What is very interesting about trapped ions, because you are dealing with light, it gives you a lot more possibilities in terms of connecting your qubits. Essentially, you form some sort of laser array where your ions or atoms get trapped within here. This is a visual expression of those. And you can use laser beams of different wavelengths to actually control and trigger different excitations and entanglements between the atoms inside your array. This means that you don't necessarily need very large number of qubits because you can entangle them in ways that are not possible on solid state technologies. And that is what you see in these diagrams over here, which look somewhat like mandalas. This is, I think, their 21 qubit system, and they've already shown an all-to-all connectivity. Now, what that means is every single qubit in this array can be connected to every other qubit that you see here. Now, this is something that is not at all possible with silicon or semiconducting technologies because they rely on conduction lines and RF lines to connect them. And it is simply not possible to have full connectivity in such a setting. However, with this type of technology, it is, and you have complete connectivity. Every single qubit can speak to every other single qubit in your array. So complete connectivity is one of the massive advantages for trapped ion systems. Now, as you can see in this diagram over here, IonQ is another example of how this technology has massively increased in capability over just the last few years. This was last year, 22, and this is a roadmap projecting into the future where they expect to be. Now, IonQ have released their own metric of comparison called an algorithmic qubit. This is not necessarily the physical number of qubits that you have. This takes into account how many qubits are in the system that are capable of performing an algorithm. This means that they are error corrected, which is something that they hope to achieve within the next 2 to 3 years. And as you can see, this number is scaling exponentially. So a very interesting technology, and they have their own cloud-based system, so you can access this via their website. However, this is one of the QPUs that is also available on Amazon's AWS bracket. So Amazon have a platform where you can access at least 3 or 4 different types of quantum computers, and you can perform logic operations, and you can compare the performance of these different systems. This is obviously for a price. One of the last qubits that I mentioned in the beginning is the Majorana qubits. And this is the direction that is being heavily followed by Microsoft. Now, as I mentioned before, Majorana fermions, the principal quantum state that this technology is based on, are very exotic particles which can exist in certain scenarios. What you are seeing in this schematic over here is an actual nanowire device which has been contacted, a semiconducting nanowire, which has been contacted with a superconducting island. When you combine superconductivity and semiconductors, you can actually start forming these Majorana particles. And as you can tell, this is a very complex device with several gates, sources, and drains in order for you to excite this particle and then control it. And this is a schematic of what this type of gate device would look like. Tunnel gates, super gates, the superconducting region, as well as your semiconducting device. And basically your quantum state would sit here, and you control it with these gates. Having said that, Microsoft do not have a commercially viable product yet, because this is such a new type of technology and very difficult to control. They have some teething problems in scaling the system up and actually the development side. Now, moving back to our hybrid solutions, Xanadu have the full stack system, as I mentioned before. What is very interesting about this is they have software that is a proprietary software that you can access that runs their quantum system, and they are heavily dependent on quantum machine learning. So some of the world specialists in QML actually work at Xanadu to look at hardware-specific operations that you can perform. As I mentioned before, there is some component of cryogenic cooling, which is basically their detectors. However, everything else with regard to the control and measurement of their quantum system occurs at room temperature. So in terms of footprints, this is a lot cheaper to develop and a lot smaller compared to the larger QPUs. Having said that, these type of quantum processors are still in their infancy in terms of number of qubits, and I think that they only have about 20 to 30 qubits available right now. This is less than a third of what IBM have released last year. So in terms of output, they are lagging behind. PsiQuantum, on the other hand, as I did mention, they do not have a single commercially available product yet and expect their first product to only be out after the next 5 years. They are not targeting the NISQ era market. They are moving directly to fault tolerance, hence their desire to develop a 1 million qubit system. So where do we sit with the current technologies? What can we actually use them for? One of the biggest problems with the NISQ era, and hence the name noisy intermediate scale systems, is that the qubits themselves are noisy. They decohere very quickly. This means that you are limited in the size of the quantum algorithm that you can actually operate. This also means that you have lots of errors that creep in because of the decoherence of the qubits. One of the problems of this is that it limits how big a quantum algorithm and obviously the logic operation that you can compute on this. And basically, we need a lot more qubits to perform the same type of logic operation, because instead of basing this on physical qubits, we now need to start thinking about logical qubits, because you have to perform the same operation multiple times and have error correction and error mitigation protocols put in place before you can actually regard your system as error-free. What you can see in this schematic over here is a representation of the number of physical qubits, how they are scaling, and the physical probability error, which obviously you want to reduce. Now, systems today are around here, 2020, 100 qubits. One thing that's very interesting is we have already passed our first couple of instances of quantum supremacy. Now, quantum supremacy is a term that we use to describe when a quantum computer can perform a certain task faster or more efficiently than a supercomputer or a classical computer. There are already 3 instances of quantum supremacy that have been announced. 1 by Google and 2 by Chinese universities that deal with boson sampling techniques. So this is a very interesting time that we are living through. We are passing the threshold of classical simulation. We are seeing instances of quantum supremacy. The number of physical qubits that we are now have access to are getting to a point where we are able to move past physical error probability barriers. And now we start seeing us approaching some form of useful computational tasks. And this is I think, why there are so many people looking at application space right now, as well as novel qubit or algorithm development, which is a major topic of over the next 3 days. So how do we move beyond noisy systems? How do we reduce errors in qubits? Well, one way is to increase the number of qubits that you have in the system. However, this is very difficult to do for multiple reasons. Sometimes there are limitations on how the qubit circuits themselves actually fit together. Other times there are limitations on the control and hardware side. For example, this is an image of the insert of a dilution fridge that cools the system down to millikelvin regime. As you can see, when you start approaching hundreds of qubits, these are all hundreds of RF lines operating at high frequency. The dissipation that can occur here is enough to increase the temperature of your system and cause errors in the qubits themselves. The more qubits you need, the more measurement lines you need. The bigger your footprint gets, the bigger the fridge is. This is not a sustainable way of doing this. However, more recently, researchers have been looking at more efficient and elegant ways of controlling large number of qubits, bypassing the need and requirements for this massive infrastructure. This is called Cryo Cmos. Good examples of this are corporations such as Intel and Microsoft, and basically reducing the overall footprint from this to something like this by placing a CMOS or semiconductor technology within the dilution fridge close to the qubits. This drastically reduces the number of control lines that you require for the qubits, going from hundreds or thousands to less than 10. And you have some sort of classical logic processor down here, which will be able to interface with your qubits, control them and operate them and perform all of the logic processing, having very minimal room temperature electronics. This is one of the major ways to develop fault-tolerant QPUs because you will be able to scale up your qubits a lot faster without necessarily having to worry about all of the disadvantages of the large footprint solution. Also, you have qubits being coupled to electronics at a much closer level. So any type of error that would have existed because of the measurement line is essentially mitigated. So we essentially believe that this will be a way to have more efficient control of qubits with a much smaller footprint, driving down the cost as well. So areas that we expect Cryo Cmos to play a role in making quantum computers more efficient or scaling them up. This is at the quantum layer. So for example, how do you actively connect thousands of qubits together? Well, one way would be to have clusters of qubits, which then connect to CMOS technologies on the chip, and then controlling the CMOS technologies and allowing them to interact with the individual qubit clusters. This allows for a high fidelity control and readouts. Another very interesting area is Cryo Cmos design, where we look at ways of reducing the power consumption of your Cryo Cmos in order not to interfere with the quantum states of the qubits. Of course, one of the best ways that this is allowing for qubit scale up is because of the interfacing, quantum classical interfacing. As I mentioned before, reducing the number of lines that you have and everything being controlled by the Cryo Cmos. Having said that, currently, there are still a couple of gaps between the available hardware and the requirements for some of the algorithms. This is because in the early days, a lot of the work on algorithms was done purely theoretical because we did not have access to quantum systems. So high-end theory typically required hundreds of thousands of qubits. However, what is very interesting is because we are now approaching or have breached the 100 threshold gap, we are starting to look at regions where there are a number of different types of quantum algorithms that are within reach, and we can already start studying. Examples of this are variational quantum eigensolvers, quantum optimization algorithms, quantum phase estimation, and a number of others. So as I mentioned before, this is a very exciting time for us because a lot is happening. Now, I've spoken a lot about the hardware so far, But this is only half of the story. As Ganesan and previous speakers did mention, a very big aspect or drive of the ecosystem right now is within the software and the application space. Beyond hardware providers, software providers for quantum computers have also become a very interesting point for venture capital and have raised in excess of $1 billion over the last 2 to 3 years. This is a very hot area, and many startups are now in existence that look specifically at software solutions. Having said that, the bulk of the players have their own in-house software and hardware development, with very few of the players focusing primarily on hardware. This means that software is definitely one of the first aspects or sectors of this ecosystem that we expect to see massive boom and a large number of job opportunities within the near future. Having said that, there are a large number of relatively well-funded startups already in existence. These startups are actively sourcing or looking for talent. They have summer schools as well as hackathons, and are always looking for enthusiastic students, as well as participants or PhD holders as well, and generally people from any background. So anybody interested in algorithm development and actual software or the ecosystem around quantum computing, I highly suggest that you take a look at some of these companies. This is also very international space right now, with providers being in existence all across the world. Some of these software providers or companies have very strict domains or sectors within industry that they work. For example, finance is a very, very hot topic right now. There are companies such as Multiverse Computing, which strictly study finance, as well as Quantum Computing Incorporated. However, there are others that have very broad area focus, such as Zapata and QCware. Companies like this actually put a lot of emphasis or focus on trying to find individual solutions for clients that are interested in starting quantum computing research programs. So they will identify key issues around implementation of quantum algorithms tailored to specific applications, which is really interesting. Of course, this is not an exhaustive list, and there are several other domains and industries as well as startups that are available right now looking for talent. So as I mentioned before, if you are somebody that is interested in this area, in the sector, there is a lot of opportunity out there right now. And these are very well-sourced and funded companies as well. Most of how this is actually generating funds right now, we are still within the application space. So development of IP, research, obviously, patents, as well as consultation, and developing actual software products and platforms such as APIs and SDKs. So this is what is happening on the software side right now. Now, as I mentioned before, when we start taking a look at the various quantum systems that we have access to within the NISQ era, two of the biggest players, IonQ with trapped ion systems and IBM superconducting systems, already have several very impressive quantum computing platforms. What I've overlaid on this graph now are some examples of where we see number of qubits, physical qubits, being related to certain algorithms that are being studied right now. And as I mentioned, we have already crossed a certain threshold where certain types of applications and algorithms are within reach. And that's why this is such a hot area right now. A very good example of this is quantum machine learning. This is because this is a quantum classical hybrid technique, which basically means that some of the machine learning is done on the classical side, and you either incorporate quantum data or use machine learning to drive the quantum system in some sort of reinforcement learning way. And we'll get to that in a bit. So because it has this classical counterpart to it, has meant that its readiness for small-scale systems has been reached a lot sooner than other types of algorithms. And over here, I've just taken a look at some of the most popular algorithms that we know of. Variational quantum algorithms. This is used in optimization problems. And then things like polynomial time circuits for Monte Carlo simulation, which is a very big problem in finance. And then things like optimization algorithms. And again, these are used ubiquitously in various industry sectors, from chemistry, pharmaceuticals, finance, etc., etc. We are not yet at a universal quantum computer. That will be very interesting for quantum encryption and code breaking, specifically things like Shor's algorithm, which I think other speakers will be dealing with in subsequent talks. But as I mentioned, we're in a time right now where things are pretty interesting in the quantum ecosystem. So even though we're still limited in some way by the hardware, there are various types of industries or applications that are being targeted right now. This is everything from pure research in physics and simulation, as well as chemistry, to more applied fields like cryptography, code breaking, factorization, finance as well, portfolio optimization, risk analysis, arbitrage. Even things like predicting stock market crashes are seriously being investigated right now by various players in the space. Pharmaceutical industries are heavily invested in this, as well as drug companies trying to identify things like peptides and molecular interactions of folding. However, this is at a very low readiness level right now, so very exploratory kind of work. And then obviously, as I mentioned before, artificial intelligence and specifically machine learning is a very, very ubiquitous and highly researched field right now. So as we said, there are some serious limitations that we have with the qubits at the moment. We simply don't have enough and we need to scale them up. We also need them to be faster, more efficient, and better control protocols for us to identify errors and also run the quantum logic. This means that we need to understand noise and dephasing effects a lot better, and the overall physics in these high number or high density qubit arrays. And essentially, we need to work around ways of mitigating such errors and developing fault tolerance. Now, one of the big questions right now is, how can AI or machine learning help to solve these problems? And the answer is there are several ways, both on the hardware side as well as on the software. Hardware side, there are already several instances of corporations looking at automated measurement and qubit control protocols, where AI will actually be running the individual qubits or clusters or even algorithms, identifying their probability, and based on the statistics and the probabilities that you get from the output, will be able to optimize some of the control parameters. And then in feedback loops, start looking at mitigating errors. AI can also be used for qubit characterization. This is even using image recognition. And then obviously error control at the qubit level. On the software side, there are obvious overlaps between quantum algorithm and probabilistic neural networks. So most of this has been delved at in a way of trying to identify errors using neural nets. Now, going back to measurement and control optimization. For what you're seeing here is an example of a typical measurement setup that you would have on a quantum computer. The bottom right is your dilution fridge, which cools down your system, where you have your qubits. Then you have some room temperature electronics, typically high frequency, operating at the gigahertz. And then you have your measurement line inside the fridge, and eventually your computer somewhere at the low temperature. And this is representing the qubit state. You zap it with some sort of microwave pulse, and you can select which state it sits at, a superposition of 1 and 0, any point on this block sphere. And you entangle them, and you can rotate them, and then read out what your eventual state is, and this is how you perform your logic. So this looks something like this, exciting or allowing your qubit to move around. This is basically a two-dimensional mapping of what the state is. based on your readout line. Now, as you can imagine, this can be very chaotic, and sometimes when errors creep in, this will not be at all what you expect it to be. So having this visual outcome or this data set is something that can be monitored through Coleman filters and other type of machine learning techniques in order for you to develop ways of mitigating the error based purely on the hardware. So we move from phase space to heterodyne mixing scheme. And this, as I mentioned, gives a very good 2D data set and can be fed into some sort of machine learning technique. Typically, they've already used a linear discriminant analysis, LDA, but there are a number of more advanced algorithms being studied right now, such as quadratic discriminant analysis. What they've seen is that they're able to increase the fidelity of qubits by using this technique. Now, fidelity is basically a way of giving us an idea of the quality of the type of qubits that we have and what we're using them for. So that's some very interesting progress coming from IBM themselves, Jay Gambetta. Another example of using qubits and machine learning techniques is in identifying and characterizing the error. Now, I've mentioned Majorana qubits a number of times, and what I keep on going back to is that these are very difficult quantum states to use and incorporate in devices. The physics behind them is very exotic. They're not easy to understand or to characterize in a device setting. And one way that we can do that is by using quantum machine learning, or at least machine learning protocols. And again, this is because the readout that we get is very well spatialized data. So either through the image of our different quantum states and using machine learning to detect variances in this or the spacing between these different quantum levels, we'll be able to understand more about the physics of the actual quantum device. So there's a lot of data processing that can be coupled to quantum computing. And this type of stuff is specifically very interesting for hidden Markov models, which is heavily used in machine learning techniques. Another very good example is trying to suppress stochastic decoherence. And this is done through predicting future evolution of qubits. So if you have some sort of classical machine learning system, which is continuously learning about how specific qubits operate, it gets pretty good at being able to predict what the qubit will do in the future. And this obviously is highly important for systems where you are running a very large number of qubits, or qubits that require very fine control, or the requirements of understanding and reading out qubits at a very high level. So you can actually prepare a feedback loop, train your neural net or whatever type of machine learning you're using, and based on its parameters, start tweaking the operation of the qubits, and in a feedback or iterative technique, learn something about the qubits and hopefully predict how they will be operating and mitigate any errors that can result from noisy qubits. So we expect some sort of speed ups in the measurement time, and this should also allow errors. As I mentioned before, even image recognition capabilities of AI can be useful for qubits in quantum systems. What you're looking at over here is a very good example of a technique we use in nanotechnology called STM or AFM. So this is basically a type of image recognition technology that allows you to map out systems at a very small scale. This is 5 nanometers. So what you can see here are actual individual atoms that are used in semiconducting technologies. You can dope a system and place the atoms inside a host crystal, and you can map them out and identify where they are. You can then use AI or machine learning image recognition software to try to identify what is happening at a localized region of your qubit, and therefore understand the quality of your individual qubits. This is a schematic of the device. This red dot over here represents the island where the single phosphorus atom would be sitting. These over here represent islands or contact islands, which allow you to control or interact electrostatically with this qubit. What you see on the right here is an actual STM image of the waveform of such a phosphorus atom. Now, because depending on where these atoms sit in the lattice, they will have different environments. They will have different nearest neighbors and different points within the host lattice. This means that their wave function will also be affected by this environment. If we can map the local wave function and learn something about it through machine learning techniques, this gives us a very nice way of categorizing the quality of individual phosphorus atoms that are used in these type of qubits. This is a technology that is already being heavily investigated, and several publications have already come from this. Here's an interesting paper for anyone interested: Framework for Atomic Level Characterization of Quantum Computers by Machine Learning. So very active area and very creative way of integrating machine learning to quantum tech. As I mentioned in the previous section, in these phosphorus arrays, depending on how many atoms are close to them, how many other qubits in this array, you can have a various multitude of types of symmetries of this image. So you really do need something powerful like convoluted neural network in order to learn what is happening in these type of devices and technologies. So just using visual imagery that we can get in the lab, we're able to train neural networks and identify the quality of these qubits and understand how good they are for useful quantum computing. Having said that, that comes to the end of what I was talking about in terms of hot topics right now on the hardware, also incorporating machine learning. The next couple of slides will just be some of the aspects of my own research and what I'm looking at the moment. I'm currently running some quantum machine learning as well as quantum algorithm development using IBM's Qiskit. This is primarily quantum phase estimation and specifically for risk analysis as well as other aspects in finance. So this is building on information that is already available on Qiskit and trying to develop and create novel types of ways of using the commercially available algorithms out there on IBM Experience. This is also being coupled to some AI interfacing, for example, support vector machines, and we are hoping to try to pivot this type of intersection for financial markets. So anyone that's interested in these type of projects, please do reach out to me. We're always looking for interesting collaborators or people that would like to be involved in this type of research. Thank you very much. That's everything from me. If you're interested to know more, I run a small blog called Quantum News. You can follow it online, post once a month, and on various aspects of applied quantum computing, hardware to algorithm development, and any hot news on the industry. So feel free to reach out. Thank you very much.
Thank you, Mr. Chris, for the wonderful presentation. This has got a lot of details. One can, suddenly, take home and, and start the quantum kind of, the journey with this. Certainly, I appreciate all your effort put on this. I will open up for questions for next three minutes. Sir, Vincent sir, actually, like any questions from your side? And also there are questions from the chat window, looks like.
Yeah, sir, I think you can ask for go through the chat window. It's an excellent presentation by Chris. I think with the last 3 months, I think I am just entering into the quantum, and I am trying to see what are the research work is going on in the quantum computing with IBM and the Google. And what I have seen, Chris sir has excellently explained everything. And I think in the machine learning and as well as that CNN, and the students, the researchers, now everybody is working about the deep learning and how in classical computers, how this could be taken care about the genetic algorithm and neural network has been converted while using the qubit, how fast and how accuracy we can arrive the results. And I think Sir has given the reference paper to the researchers and as well as the faculty members. Definitely you can learn more about from the Chris sir. Thank you very much, sir, Chris sir.
Oh, thank you. Thank you once again. And also, Dr. Chris, could you explain about the quantum hub, which we want to set up in many colleges and the other places? Is there a time you can spend 1 minute on that and see how we can collaborate and jointly set up the lab?
Yeah, definitely. I think that there's a very big importance right now for developing interaction and also things like Quantum Hub. As I mentioned before, this is an emergent field. We need more people because there's going to be a skill shortage in quantum computing. This is a highly specialized area. And one thing that we're seeing in the industry right now, there are various aspects to the ecosystem that need to be filled by people who know something about quantum computing. Now, this can be on the hardware side, it can be on the algorithm and software development. However, in terms of business aspect, venture capital, and intermediate people, blog writers, the quantum education ecosystem, there's just so much opportunity right now. And I think quantum hubs are one of the ideal places to get people together to start interacting and just learn a little bit more and finding their way in this ecosystem. So it's a very good idea. And I think it's a very valuable endeavor.
Yeah, sure. Thank you, Dr. Chris. And team, the universities, can work with us and set up a hub, and we can, work on a plan too. Looks like people are asking already how to register in the hub and all the stuff. We will get back to you. What is that we can do, with the PSNA as part of the hub. And there is another question, Chris. What is the impact of data science in quantum computing?
This is a very good question. And I think it's difficult to answer. If you take a look at the research side, you will see a lot of very interesting papers, especially recently, looking at the intersection of big data and how people are trying to integrate the two together, data science and quantum computing. I would say that I think most of the intersection is actually through machine learning. I think this is one of the biggest areas for this. The reason for that is a big question that gets asked is how do you actually take classical data, especially in large data sets, and how do you map that onto a quantum computer? And there are various ways of doing that. You have to first represent all of your data sets into some something in the phase space or mathematically change it. There's some sort of mapping involved. And we call this creating the quantum feature space. So there are various aspects to the research on how to actually integrate data or represent data on a quantum computer. This is a highly active field. So in terms of research, tons of work. Obviously, this is also very interesting for application and industry. So I would say that this is, I don't have a direct answer, but I say it's very important and it's very actively being researched right now.
Sir, this is Dr.
Thank you.
Question to Chris, sir. Sir, I think when we come across the IBM Quantum's lab, I think they are providing some of the stuff to the researchers, and I think we've gone through some of the papers and they related to the optimization. But in the same way, the Google also they're providing their own stuff while working for the image processing and other things. So how the researchers or how the new people entering into the quantum computing who wish to do some classification algorithm or the image classification, whether they should go with only as from the Google or the IBM, how this the paper and the accuracy will be taking place when publishing a paper in the good journals.
That's a very good question. Look, I think when it comes to the different providers, that is up to the individual. I mean, whoever you feel comfortable with or whichever API you like the most, you should just be aware that the various providers have a bias towards certain sectors. You mentioned Google. Now, Google AI labs are very interesting because they do a lot of machine learning, quantum machine learning. You're very right. However, if you take a look at their quantum computing applications, they are heavily focused primarily on material science and energy. So you will not see them doing a lot of things around finance. So I think it depends on the individual. I mean, if there's something specific you want to look at, try to find a platform that is investigating or at least has those resources and go that way. Having said that, I think that IBM is one of the most accessible systems. The platform is open, so anybody can register for that. And there's a lot of information out there, as you mentioned, papers, textbooks, and even YouTube clips on how to use Qiskit, how to run your first algorithm, and how to start preparing quantum circuits. So I think the first step is definitely getting more acquainted with it. And then one of the big questions right now that everyone is asking is, what is the good application of quantum computing? And I think this is part of your question. How do we actually use a quantum computer properly, and what are the advantages? And this, again, is an open question. We don't know the full capabilities of quantum systems yet, and that's why we are studying them. So again, difficult question to answer, but I think there's a lot of possibility or potential for research on this.
Okay, thank you, sir.
Yeah, there are a few more questions, Dr. Chris. Actually, can you just take a look at the chat window?
Yeah, so I see that there's a question specifically on applications. I think I did mention this in one of the slides. I can tell you that the most active areas in industry right now are finance, chemistry, energy sector, security, and then machine learning, which is used across all of those. There are obviously a couple more smaller ones, but I think those are the main players in terms of industry. I see that there's a question here about how to check success of ALD deposition, selective etching. I'm not sure about that. That sounds like a very specialized type of application. I don't know much about how ALD is being checked anyway with classical computers, so I'm not sure about that type of simulation. And how far QPU differs from GPUs. I'm not really sure on that anyway, because I'm not a GPU specialist, so difficult for me to answer. I can tell you that in terms of the QPUs and intersection with machine learning, generally GPUs are being used anyway for a lot of the neural network side, and then your QPU only performs certain aspects of the logic processing. So for example, this machine mapping or some sort of optimization part will be on the quantum side, and then that information you will actually train your neural network, and which uses the GPU. So the two of them are quite important, but ultimately the difference is coming from the hardware, right? A QPU is fundamentally different from a GPU in terms of what it is built on. And there are various types of QPUs out there, as I did mention inside the talk today.
Yeah, thank you. Thank you, Dr. Chris. Once again, I know it's too late for you. Thank you for staying with us, till like 11:37 Indian time. And really appreciate it, your time. And I look forward to work with you on several the workshops, probably creating a diploma in quantum and setting up hubs all over the world. I enjoy working with you also in the past and the present, and also in future. Thank you very much, Dr. Chris, for the wonderful time you spent on this.
Thank you, sir.
Thank you.
Great. Thank you all. Thank you all.
Thank
Bye.
you.